Yeah, we are considering the detectors for liquid chromatography. Okay, there are many kinds of detectors. Most of them are based on spectrophotometric uh, the detection. Okay, so as I mentioned, the last lecture, the ideal detectors must have possess this kind of characteristics. Must be sensitive to low concentration of every analyte. Okay, and provide a linear response and must not broaden the elute peaks and so at the same time insensitive to change in temperature and solvent composition and small detector volume is favored. Okay, and back pressure available to prevent gas bubble formation. Okay? So let's take a look at the list of HPLC detectors. Okay, there are many kinds: ultraviolet, refractive index, and so on, and evaporative light scattering. Okay, so I would say, but the ultraviolet detector is the most widely used detector for HPLC. Okay, so we'll briefly uh, overview these detectors. Okay, the first one is based on ultraviolet absorption. Okay, uh, the most organic chemicals they take a white color. Okay, which means that they don't have any absorption in the visible region. Okay, but most of them absorb light in an ultraviolet region. Yeah? So if you use ultraviolet light, and then we can detect the molecules. Okay, the detector structure is actually is really simple here. Look at that. Here is the eluate comes in from the column, right? Then it follows this channel, and here the principle is the same as the absorption spectroscopy. Okay? Then, as you know, the absorbance A uh, equals epsilon BC. Okay, epsilon is the molar absorptivity. That's the characteristic of each molecule, and C is the concentration, and B is path length. Okay, so epsilon and C, they are already fixed, but we can change it. We can increase the path length. How? This way. Okay, and then this is a very narrow channel. Yeah? You don't need to have a the large channel because light would pass this narrow channel. Yeah? And then here it follows this channel, and then in this part, look at this part, right? This is a linear part, and then this eluate now comes out of the this part. Okay, and light, you send the light through this narrow channel. Okay, and here you put a detector. Okay, so the path length is this one from here to there. Yeah? It is long path length. Okay, so that makes detection uh, much easier. Okay, let's read this part. Light path here. This is a light path in a spectrophotometric microflow cell. This is a microflow cell. Why? Because you need only microliter your sample. One common cell with a path length 1 centimeter has a volume of 8 microliter. Okay, and 1 centimeter path length is that's the standard cell, okay, for the absorption spectroscopy. And since the channel is microchannel, the volume is quite small. It's here uh, less than 10 microliters. Another cell with a 0.5 centimeter path length contains, yeah, if we decrease the path length, okay, and then you can still decrease the volume. Yeah? And in the future, it should be possible to lower detection limit by one to two orders of magnitude by placing mirror on on both ends of the cavity here, which means that now you put a mirror, and then mirror, the light is reflected the mirror, and then go back here, while it reflected back, and then that light also absorbs. Okay, it will absorb from the the solute, and then going back and forth, and then the absorbance will increase. Yeah? Putting mirrors here, that's the equivalence to increase in path length. Okay, so that way it is possible to uh, increase lower detection limit by 1 or 2 orders of magnitude. Okay, 10 times or 100 times, we can lower the detection limit. Okay, and this is the most common HPLC detector. Structure is quite simple. A simple system employs the intense here. What kind of light can you use? That's a good question. And then mostly the intense light beam, whose wavelength is 254 nanometer. Okay, uh, this is the characteristic emission line of a mercury vapor lamp. uh, you know the organic synthetic chemists, they use this mercury lamp. Yeah, mercury lamp. Every lab, no, even in my lab, mm, I have one mercury lamp. Okay, that lamp now generates the what emission. This is fluorescence whose wavelength, this one, 254 nanometer. Okay, this is monochromatic light. Okay, then you send that light from here. Okay, and then most the organic molecules have broad absorption band in UV region, so most of them now absorb, you know absorb small work rate, at this wavelength. Okay, and then it can be detected, by the detector. Okay? That is the most common the wavelengths, or other discrete UV ultraviolet wavelengths from zinc or cadmium vapor lamps. Okay, uh, but sometimes the molecules don't have any significant absorption at this wavelength. In the case, you must have a different the light. Okay, from different lamps, like zinc or cadmium vapor lamps. But mostly, this one, mercury vapor lamp, is widely used. Okay, more volatile instruments have versatile instruments have broadband deuterium, xenon, or tungsten lamps and a monochromator, so that so you can choose an optimum wavelength for your lights. Okay, yeah, this makes the system quite complicated. Okay, instead of using a monochromatic light, but you can use any light, by selecting the specific wavelengths using a monochromator. Okay, that makes the system quite complicated. But most HPLC instruments you know are equipped with this type of detector. Okay, and the other detector is a photodiode array detector. Okay, photodiode array. The photodiode means that some diode are very sensitive to light. Okay, here look at that. Um, this is a sample. Here is a sample flow cell. This is kind of uh, this is structure is the same as UV visible absorption spectrometer. Okay, here is this is a photodiode array, and then the light source here is this is a deuterium lamp. Deuterium lamp generate UV light, broad UV light, continuous UV light. And then that the light now is after the here is the monochromator, and then it it enters this sample cell, and then after this sample cell, it is detected by this photodiode array. And the beauty of this type of detector is that you can obtain the spectrum. Yeah? You can obtain the spectrum because here this deuterium lamp now is using this monochromator, yeah? And then whole wavelengths now pass through this sample cell, and then is immediately whole wavelengths now detected by this photodiode array. This diode array has this is a linear type. It has many photodiodes, okay, and then each diode corresponding to a specific wavelength. Okay, yeah, look at this one. Yeah, this way you can get this whole spectrum. This is anthracene, yeah, separated from HPLC, yeah? And this one, uh, this is the detection of at a specific wavelength. Okay, so this is chronogram, and then if you are sure if you want to measure the spectrum of this peak, and then you use this photodiode array detector. Okay, and then this one, since all wavelengths in the signal uh, are collected, are detected at the same time by this photodiode array, and then you can very rapidly get the spectrum, whole spectrum for this peak. Okay, yeah, this is the anthracene spectrum, and you need high quality detectors. Okay, because they provide full scale observance ranges from 0.005 to 3 observance unit. Okay, yeah, this is important. You can have full scale observance. Okay, that's the characteristics of photodiode array detectors. Okay, and then also observance range, wow, down to 0.005, okay, up to 3 observance unit, and the noise level is near 1%. Okay, quite good. The linear range extends over 5 orders of magnitude of absolute concentration. Okay, it has 5 orders of magnitude of linear range. Yeah? And UV detectors are good for gradient illusion with non-absorbing solvent. Okay, this is good for gradient illusion. Okay, yeah, but system is quite complicated. But I've never seen this kind of detector. You know, HPLC. Yeah, and another detector is the evaporative light scattering detectors. Okay? It has definitely certain advantages. Okay, this detector is based on light scattering. The light scattering. That is the light is a wave. Okay, light is has a properties of a wave. It's a wave and a particle. For light scattering, this is the properties of a light as a wave. The light is scattered by particles. Okay, um, so for the better scattering, the light wavelengths, when light wavelength is similar to the particle size, and then you can have a very strong scattering. Okay, so this light scattering detector, can be can detect any particles. Okay, and then okay, let's read here. These detectors respond to any light that is significantly less volatile than the mobile phase. Okay, yeah, if your light is not very volatile, then it exists as a maybe a particle here. It's a small droplets, and then these small particles now scatter the light. Okay, and then you measure the scattered intensity. Okay, you look at this detector structure here. Now here, your your illuent now pass through this nebulizer, okay, nebulizer. And then using a nitrogen gas, and then this one, it your illuent now is it what makes your eluent and becomes this type of fine the mist, okay. And yeah, that's what this nebulizer uh, does, okay. And then here it contains uh, this one here is a small droplet, yeah, this is your analyte, yeah. And also and you know in the mobile phase, yeah, but here mobile phase is quite volatile, okay. The condition for these detectors is that your analyte must be less volatile than the mobile phase, yeah? Mobile phase is quite volatile, right? It doesn't exist as particles, right? The they exist as a molecules, okay. But molecule size is so small. It's so small, smaller than the light the wavelengths here, yeah, usually laser beam is used, so light scattering effect is almost zero, okay. uh, the when you think of light scattering, you may uh, consider the colloid particles, okay. One of the colloid the characteristics of colloids is the scattered light, that is called the Tyndall effect, yeah? And since colloidal particle size is quite similar to the light wavelengths, and then it gives us a very strong scattering effect, okay? But the molecules, yeah, the size particle size is quite small, much smaller than the wavelengths, okay. So virtually molecules don't have any scattering effect, okay. So here, although now this mobile phase and your analyte now becomes kind of what the mist, right? But the solvent mobile phase not doesn't scatter the light, only the sample droplets scatter the light here, okay. So solvent evaporates from the droplets in the heated dripped tube, leaving a fine mist. Yeah? This is important. Fine mist. The particle size is big enough to the scatter the light. Okay. The fine mist of solid particles to enter the detection zone at the bottom. Okay. This is detector zone, and response is related to mass of an analyte, not the structure or molecular mass of the analyte. Yeah, this is important. Yeah. So I think this is empirical equation for these detectors. Okay. Log A is the area of the signal here. You see, area of the signal equals A plus A is constant and B times log M. M is mass of an analyte. Okay. So as you may know that scattering depends on the size of the particle, okay. Not size of particle may be approximately the proportional to the mass of an analyte, okay. The scattering effect it doesn't have any relation with the molecular structure, okay. So with this detector you can detect any molecules, okay, even though the molecules that don't have any UV absorption, okay. And then this figure compares the detection, compares the chromatograms depending on different detections. These two, yeah? Actually, the textbook, if you read the textbook, you may know that the 5 components actually are there. Yeah? So, but with UV UV detectors, whose wavelength is 232 nanometers, you detect only 1 and 2. Okay, actually this one, maybe here, I think this is the non retaining species. So but if you use the UV light at 205 nanometers, and then you detect more peaks, okay, here and there, right? Which means that some molecules don't absorb the UV light at 232 nanometers, okay, but that that molecules but absorb UV light at this wavelength 205 nanometers, okay. Yeah, this is the uh, what this advantage of UV detectors. Yeah? Simply we assume that most molecules absorb UV light at this wavelength. Yeah? For example, 200 let me see, uh, 254 nanometers, but some molecules don't, okay. Yeah? But still, if we use this evaporative light scattering detector here, and then you detect more, yeah, more peaks. Look at that. Here it says another one, this one, and this one is very visible. Okay, mm. Why? Because this detector, doesn't care where that molecule absorbs UV light or not. Okay, it only detects the particles. Okay, so that's why it gives the more peaks. Okay, and also this background signal is quite constant, quite small, but with this UV detector here in this area there is a sloping background. Okay, with this one this mid one shows more severe slope background. Yeah? This is not a real signal, but this is due to the solvent gradient. Okay, here in the usually in a HPLC experiment you use a solvent gradient. Okay, so this reflects solvent gradient. So but the unexperienced people may think, oh, there is another another peak, right? But that is not true. Okay, and also there is one big advantage for this light scattering detector, which is that no peaks associated with the solvent front. Okay? Sometimes, or I would say many times, you observe this peak. What this one goes up, and this part is rather the going down peaks, right? This peak, this peak are often observed in uh, HPLC. Okay, and then this first one is TM, not retaining the peak. Okay, but why? Yeah, there is a peak going down, right? This is called solvent front. Okay, solvent front. Yeah? This solvent front. Yeah, this is these peaks are not real. Yeah? These signals arise from changes in the refractive index in the mobile phase due to the solvent in which the sample was dissolved. Okay, now sample is mm, dissolved in mobile phase. Okay, actually samples are dissolved in a solvent, and then now you inject sample with the solvent into the column, and then now that sample is carried away by the mobile phase. So here this you know, some peak is going up and this one is going down, right? And then this is the due to the refractive index change. Okay, because your mobile page has a certain refractive index, and then your solvent also has a refractive index, but they are not the same. So that is reflected in the solvent front. Okay, but here this one was this figure was taken from the figure 13, but with evaporative light scattering, this part is never appeared. Okay, This change displays the ultraviolet detector signal at the time Tm here required for unretained mobile phase to pass through the column. Okay, and if a signal is eluted close to time Tm, it can be distorted by the solvent front peaks. Okay? And then here, this figure shows that the molecules 1 to 3, yeah, 1, 2, and 3, they are appearing after the this peak, okay, Tm, after this solvent front. But some molecules may be eluted very earlier, uh, you know, maybe in this time scale. In the case, type peak, you know, cannot be precisely determined. Okay, yeah, because of this this one solvent front peak distorts the signal. Okay, an evaporative rapid scattering detector has no solvent front peaks. Okay, in this way, yeah, regarding this solvent front peak, yeah, this lattice evaporative lattice scattering detector has a certain advantage. Okay, okay, let's stop temporarily here.